Hello and welcome to this presentation related to customer or design requirements and the development of a product design specification. The object of this presentation is to provide you with an insight into typical customer requirements for engineering products and how to go about developing your own product design specification. Here's a brief overview of the table of contents for the presentation. Essentially, we commence with an overview of customer requirements and the associated product design specification, acronym PDS. We then consider some general guidelines related to PDS preparation, and a structure for the PDS is proposed. The next section, which is the largest section of the presentation, relates to design requirements. In this section, we outline a whole raft of design criteria which could be included depending on the product or the system under consideration. There are no specific order, but we commence with the performance requirements for our product, process or service. Then we have ergonomics, human factors. 3, concerns environmental issues. 4, maintenance maintainability. 5, target product cost. 6, transportation, that's referred to as shipping. 7, manufacture and the quantity involved. 8, aesthetics. 9, legal implications. 10, health and safety, and so it goes on. So this is the first 14 design requirements on this slide. And the table of contents continued. Design requirement 15, manufacturing facility. 16, size. 17, weight. So it goes on to 32, disposal on this slide. And our table of contents continued. Requirement 33, public acceptance, through to 39, related to quality assurance. And this is not a definitive list, but hopefully will be useful considerations to help you generate your product design specification. And for your reference, here are the approximate start times if you wish to jump to certain sections of this presentation. An overview of the customer requirements in PDS, which is around 3 minutes into the presentation. The general guidelines for PDS preparation, 4 minutes, and then the proposed structure for a PDS commences 11 minutes into the presentation. An overview of design requirements commences 18 minutes into the presentation. Thereafter, the individual requirements such as performance, ergonomics, environment, etc. commence at the time stated. This slide shows requirement 1 through to 14 for packing, which commences 40 minutes into the presentation. Please note that all times are rounded to the nearest minute. Table of contents continued. And here are the approximate start times related to design requirements 15 through to 32. And here are the approximate start times for requirement 33 through to 39. Times rounded to the nearest minute. So let's review customer requirements and the product design specification, PDS. So in order to provide a successful design, it is essential that the requirements of the customer are met in full wherever possible. It is always desirable to produce a specification expressing the customer requirements, so it's very important that time is devoted to consultation with the customer, as we must ensure the customer needs are well understood and, if necessary, to agree amendments or to reach a compromise dependent on the circumstances. Requirements and PDS overview continued. So in essence, a specification is a listing of all the parameters essential to the design. Generally, customers list their essential values as part of their requirements, but each value must be examined very carefully before transferring into the actual specification. Thus, the design specification should always be formulated by a design engineer or team of design engineers. Here are some general guidelines for PDS preparation. So firstly, the PDS is what's known as a control document. It states the specification that's to be achieved, but it is not the achievement in itself. The PDS is essentially the foundation document on which all design work, manufacturing, installation, test, etc. is based, and so it's a document to which all stakeholders will reference and work towards fulfilling the requirements specified. 2. The PDS is a user document for use by many people in industrial situations, and these days possibly in many different countries. Therefore, it should be written clearly and succinctly. So to ensure clarity and succinctness, Here are a few considerations. We should never write the PDS in essay form. We should not use personalized terms such as I, me, we, us, you, etc. Or indeed avoid short forms such as shouldn't, couldn't, wouldn't, etc. We should always use concise, definitive statements under specific headings, and these headings are suggested in Table 1, we will review on a following slide. And it can be useful in practice to allow space for amendments or additions within the PDS, so we avoid crowding of the page. This is particularly useful for engineers as they read the specifications. They can add annotation to the various clauses or requirements, etc. that's stated in the document. Several headings to a page may be adequate on initial drafting, although you'll find that professional PDSs may ultimately have many pages per heading. Take for example referencing. We may start your document with a few references on one page, but professional documents may have references spanning many pages. Specifications, for example, for aircraft, for water treatment plants, etc. can have pages and pages of specifications that have to be complied with. Also, we try and write the product design specifications as best we can to be user-friendly. That's not always easy with such a formal technical document, but certainly it's something we should endeavour to do. For example, using lists of figures, lists of tables, maybe lists of acronyms, lists of specific definitions, etc. Our general guidelines for PDS preparation continued. Item 3. So from the outset of PDS development, endeavour to quantify parameters within each section. Sections of the PDS might relate to weight or to cost, manufacture, ergonomics, aesthetics, performance, etc., etc. And if the extent of parameters are unknown at the time of the PDS compilation, we need to estimate a figure, or if that's not possible, clearly state in the document that the information is to be advised. For example, if the overall target cost is unknown, I would not leave cost out of the PDS. I would include a target product cost section within the PDS and either state an estimate or that the cost is to be advised. But the cost will be a central feature that all stakeholders need to be aware of from the outset. Item 4. A PDS is always unique to a new design situation, so relationships between parameters may vary. It's recommended when preparing a PDS that the starting point is varied. For example, we might start one PDS with the section for performance requirements, might start another with section for the environment or politics. The idea behind this is that varying the starting point can aid flexibility of thinking, which is required to prepare a pertinent and comprehensive PDS. But in practice, you may find that a current PDS being developed is actually founded on previous PDS that the company may have already developed. So to ensure some creativity, it's suggested here to reorientate the various requirements and section headings to help with stimulating of ideas and thinking of the way the PDS should be developed. But engineers do often refer to a previous PDS if they're available to help develop their new PDS. Item 5, the convention used. Here I'm referring to British Standard 7373, which relates to product design specifications and a proposed structure. When we're stating clauses within a product design specification, within the design criteria section, there are two words we need to be careful on how we use. For example, the word should is used for guidance clauses when no actual requirement is intended. I consider these to be optional requirements. For example, the specification may say the product should be coloured green, but it might be that the final product is actually coloured yellow because during the design process, the design engineer or various stakeholders have decided that yellow is actually preferable because it adds a safety feature to the product. On the other hand, the shall clause is used when the requirement is intended. So if we now state in the product design specification that the final product shall be light green, then we expect that the final product will be presented with a light green finish. So shall and should, be very careful how you use them when defining clauses. Just as background, the terms must and will are avoided from product design specifications. They tendency to be used for statutory obligations. So try and specifically avoid the use of must and will from your PDSs. We should always date the document and state an issue number, as this aids updating and traceability. We need to always ensure we're working to the latest issue of the PDS. PDSs usually have their own defined number that they can be easily referenced with another documentation, but the issue of that PDS number can change. And item 7, clearly and concisely document any amendments as the document is raised in issue for ease of user reference. PDSs can be very technical documents. Engineers need to read them thoroughly when working on a particular project. So it's very important that any updates are clearly documented to avoid design engineers or indeed all stakeholders from having to read the whole document again. So when you raise a PDS in issue number, we usually have a very brief statement as to what was changed in the document. For example, it might now say that a particular section has been added or a particular section has been updated, and that helps the engineer focus on the changes within the PDS without having to reread the entire PDS. So let's now consider the PDS and a proposed structure. So as I now think we're aware, the designer's description of the product or the process, system, etc. we're considering is presented in the form of a PDS. The structure of PDS, as defined in detail in BS 7373, is very briefly outlined on the next few slides. It's important to note, though, this is a checklist essentially. It's neither exclusive nor exhaustive, but it does act as a useful framework for initial PDS development. What you will find when you move into industry, that particular companies will usually have their own structures, their own styles for PDSs, but if that's not available, then BS 7373 provides a very useful overview of how to structure a PDS. So here's our table 1, which is essentially the checklist of PDS main sections. So the first page, or usually called the title page, provides identification for the PDS. It has the title of the product or the system, various reference numbers, has the author of the PDS, maybe have a box for sign and approved by, has a designation, an actual report number, has a specific issue number that gets increased every time the PDS is modified and reissued to stakeholders, and it should have a date. That will be the date of first issue, or also the dates of any raise in issue. Note the title, where possible, should provide an informative and unambiguous description of the product or the process being considered. Some documents may have a circulation list. This is a distribution list of the specification to all the stakeholders associated with the product. Then we have a content section. This is a list of contents, acts as a useful introduction to the document for the reader, and it lists the various parts or clauses, illustrations, annexes, etc. within this section. This will essentially be a table of contents, and there may also be a table of figures included, a table of tables included, even sometimes a table of equations included, depending on the type of document that's being produced. Please note a lot of these features for the table of contents or listing the table of figures, etc. can be automated within word processing documents, and it's highly recommended that these automated features are used, and that aids further updating of the PDS. The next section proposed is a foreword. This is reasons for writing the specification. This section essentially sets the scene and provides the reader with useful background information related to the project and the customer's design brief. Next we have an introduction. This states the specification objectives, purpose of the document, and can briefly summarize technical contents contained in the PDS. Some PDSs will include a section labeled Scope. This relates to the range of objectives or content included. This section provides the reader with details on the extent of the coverage and the limitations imposed on the information provided. It also provides details on the function of the product or system under consideration. For example, as referred to previously, your current PDS being developed is based on a previous PDS. For example, if you're producing electric motors or valves for petrochemical plants, the new motor or the new valve may be very similar to previous motors or valves that have been used, but care needs to be used when referring to previous specifications, because it might be that they were designed for specific applications which required unusual features within the PDS. Maybe the electric motor or the valve is designed for use within extremely cold environments, so maybe materials or sealing or lubricants that were stated within the specification were quite exotic or maybe quite expensive, but they were needed for that particular application, and that might not be applicable to the new application. So a scope is a way of highlighting any specific issues associated with the PDS for the current reader's attention, but also, as I say, when you're developing a new PDS. Not all PDSs will have a scope. Table 1, continued. Next section, BS 7373 proposes, is a reference section. This is considered to be a statement of policy regarding reference documents. I have to say, when working with my students, a tendency to suggest to them to actually use this section for the references, but it seems that BS 7373 actually includes this in the bibliography. Then we have a definition section. This relates to terms used with special meaning within the text of the PDS. It basically contains definitions. It might include complex or specialized terminology, may include abbreviations or symbols and units, such as SI units. Next we have the design criteria section. Here requirements, guidance and methods are stated. This is essentially the main body of the specification, detailing design requirements, parameters for the product or system, such as we've outlined previously, performance, ergonomics, materials, manufacturing, maintenance, safety, packaging, transportation, etc., etc. This is referred to within a later table within the presentation. Next we have annexes. These are optional to the PDS. You do not have to have an annex, but if you do include an annex, they usually relate to additional detailed technical information and possibly examples for ease of illustration, related information and references such as statutory requirements, British standards, ISO standards, design journals, codes of practice, etc. Some PDSs actually have an index stated in alphabetical order. If they're small documents, tendency not to have an index, but larger PDS is quite useful to have the index. And again, an index can be automated using the inbuilt word processing facilities. And finally, BS 7373 states what it terms the bibliography, and this relates to internal, external standards, publications referred to within the specification. As I said previously, when I'm working with technician engineering students, I tendency to use the reference section for all references that are stated within the specification, whether that's British standards, European standards, international standards, etc., etc. So I say that's a proposed structure, predominantly from BS 7373, and I use the essence of this proposed structure within my illustrations of product design specifications. In a separate presentation, I will show you an illustration of a PDS that I compiled, and you'll see there the structure I use is similar to BS 7373, but just slight simplifications included to help students with their PDSs. Let's consider design requirements. So information on what I've deemed as salient design requirements is going to be outlined on the following slides. An appreciation of the significance of each of the requirements, and in particular the various main parameters associated with each of the requirements, is essential. A compromise often needs to be established between performance and costs, as the customer specified performance may be prohibitively expensive. Take a simple illustration, it might say in the specification that in a new bathroom, all the taps and the baths, etc. is to be gold plated, but when the customer sees the cost of gold plating the taps and the baths, they may think twice. Designers must also be aware of the economic viability of meeting performance requirements, and where these are not feasible, discussions must be undertaken in an attempt to provide for a more cost-effective solution. So again, it might be that during the design process, certain aspects of the criteria are proving difficult to achieve with expected target costs. So where an overspend in finance or maybe an overrun in timescales may occur, then discussions between client and design engineers need to be undertaken. A PDS development is very often all about compromise between various stakeholders. Design requirements continued. Also be careful of over-specification of performance. This is more likely to occur in specialist one-off products, where perhaps operational information may be limited at the time of PDS development. The designers should draw upon their knowledge and experience assimilated from similar designs, or seek advice from more experienced colleagues or consultants. And I keep emphasizing the more input, the more thought, the more discussions that take place developing a PDS, the better. The urge to over-design should be avoided, and where appropriate, computer simulations, scale models, use of prototypes, artificial intelligence may all be ways of establishing appropriate performance data and so avoid any overspecification. Here's an exercise I usually ask students to undertake within a lecture, essentially to list possible design requirements for a product or system. I've just stated them here for ease of reference in this presentation. I'm going to let you review them at your own pace. We've already actually mentioned them at the beginning of the presentation. And they're in no specific order here, but I do start with performance, item 1, environment, item 2, etc., etc. You can see up to item 27 here, patents, literature, product data. I'll let you browse these requirements at your own pace. Not all will be applicable to a particular PDS, but hopefully this will help generate your thought processes related to what you should include in the PDS for your particular design scenario. And exercise 1R continued here. Now we have requirement 28 through to requirement 39. They're not a definitive listing, but hopefully will help develop your own PDS. So what I will do now on the following slides is to produce an overview under each of the headings outlining what we mean by performance, environment, life and service, etc., and hopefully to aid your understanding of what we mean by each of the requirements. Predominantly I will let you review the rest of the presentation at your own pace. So here's our first requirement from our listing related to performance. I do think this is one of the more upfront requirements to state within the PDS, if not indeed the very first requirement of the PDS. All designs related to products, systems, etc. will have specific performance requirements that all stakeholders are trying to achieve throughout the design and development process. So the performance required should be fully defined in the PDS, for example, how fast, how slow, how often, the functioning of the product, whether continuous, regular, intermittent, random, expected loading induced. There might be electrical, hydraulic or pneumatic considerations to account for, the acceptable tolerances on speed or accelerations, the rate of working required, etc., etc., all defined in the performance criterion. Note that the more complex the product, the greater the probability of there being ambiguities and conflicts between the performance figures specified within the PDS. So just for reference, bear in mind that there can sometimes be a trade-off between various requirements within the PDS, and these are underpinned by negotiation between various stakeholders, customers, designers, manufacturers, etc., involved with the design and development process. There can of course be examples of discrepancies within the PDS, and the examples shown here relate to the specification of an electrical cable to transmit 20 kilovolt amps to an underwater vehicle, when the total vehicle power requirement is actually stated as 50 kilovolt amps. Again, it's imperative that the PDS is developed with the input from a range of sources or a range of disciplines to ensure as best as possible PDS is fit for its intended purpose and is coherent and consistent throughout the specification. Performance continued. Consider is the performance demanded attainable within an economic manner. A common problem is to specify a level of performance that far exceeds the realistic requirements of the product to be designed. For example, it might be that the lifespan of the product is given as 20 years, when in actual fact customers may want to replace the item, particularly if it's a fashionable item, every 5 years. So by stating 20-year lifespan, more expensive materials might be used, more expensive sealing arrangements might be required, more expensive manufacturing undertaken, etc. So always ensure realistic requirements. From research evidence, successful design teams spend much effort in establishing attainable objectives. Remember, at the PDS stage, we're just typing the document, it's just written words, it's easy to change. A few years down the line when we're in production, it's much more difficult to then suddenly change a specification because we now realise that it's not attainable within the confines of our cost or our timescales, etc. An engineering design should perform to specification within the environmental and under the operating conditions in which it is to function. So for example, a camcorder may be reliable in that it operates very easily every time it's used, but perhaps perform poorly in that the quality of the recording may be blurred. So that would not be expected to perform to the specification. Performance continued. The design engineer needs to be careful because it's very easy to tighten up the performance specification to such a degree that if designed to meet the specification, the customer would be unwilling to pay or perhaps not even capable of paying for the finished product, even if the product was financed in the first place. It's not uncommon within PDSs for manufacturers to specify performance parameters that are not attainable simultaneously. For example, a situation that occurred many years ago, the customer wanted to place a large hole in a lifting frame for ease of storage purposes, but that hole would actually be at the location of the maximum bending stress. So in such a situation, discussions with the customer would have to take place. If they insisted on their requirements, then they'd have to be aware that that can be undertaken, but there are consequences now in terms of extra stiffening required, larger section properties, so increased weight, increased cost, increased manufacturing to achieve their specific performance requirements. Requirement 2 in our listing is ergonomics. This relates to human factors. I'll just very briefly outline these slides. The word ergonomics originates from the Greek, and it literally means the natural laws of work. Ergonomics came to prominence during the Second World War when aircraft pilots confused, for example, the landing gear lever with the flap lever, which on occasions resulted in disaster. Prior to the Second World War, little interest had been paid by engineers to ergonomic design. So considering the arrangement of tools and displays using the old steam engines, power stations and heavy process equipment, it seemed that little consideration had been given to the needs of the operator. Ergonomics continued. So nowadays all products to some degree have a person-machine interface, whether this occurs during manufacture testing, commissioning of the system, usage of the product plant, maintenance, repair, or even decommissioning. For example, decommissioning nuclear power stations will most likely require operators to be fully remote from the decommissioning environment, so design of the interfaces for the robotics, etc. is a prime concern. When considering ergonomics, we have to remember that people have natural expectations, so upward movement will switch on a device or increase its power, and these should be considered and stated appropriately within the design and the design specification. No matter how complex, sophisticated or ingenious a product, if human operation is involved, the ergonomics of the situation need careful consideration by the designer. This was an exercise I usually ask students to undertake in the lecture. Can you generate a list of various design parameters that would fall under the heading of ergonomics? You might want to start the presentation for a moment and think through design parameters where ergonomics is important. I will show you a listing on the following slide. So exercise 1G. So ergonomics is a consideration when we have controls in displays, instruments, various tools, workspace arrangements, safety aspects, environment, visual, acoustic and thermal, required height, reach forces, operating torque acceptable to the user, postures and lighting, etc. Anthropometrics. This is the measurement of physical characteristics of humans, in particular human dimensions. This illustration here showing the appropriate dimensions are actually in inches here, relates to anthropometric considerations. The third requirement on our list is the environment. Apart from the effects on the design product or system, engineers should also take into account the likelihood of the design polluting the natural environment. So for example, a nuclear reactor design, the majority of the design relates to ensuring fail-safe systems and that backup facilities exist, so minimizing the possibility of a nuclear accident which might result in ecological disaster. Another exercise here for you. Can you state further examples of where fail-safe design is essential? I suggest to start the presentation for a moment and see if you can list such examples, but a few are listed on the following slide. Exercise 1E, here are some examples, you can read them at your own pace. Exercise 2E, can you list some environmental parameters that may require consideration when designing various products or systems? An example here would be temperature. Again, if you want to start the presentation, I'll show you my listed on the following slide. Example 2E, here are the environmental parameters I've listed below. These all relate to environmental considerations. Again, I'll let you review them at your own pace. Item 4 on our listing was maintenance and maintainability. Sometimes people are reluctant to perform maintenance tasks diligently, and this can lead to failures. worn parts, or unnecessary brief operating life for a product. So maintenance includes regular inspection and replacement of parts, so our products or our systems should be designed to allow for a proper and easy installation. For successful, competitive and safe products, maintenance should be minimized and if at all possible eliminated, at least made easy to undertake. Here's an exercise when deciding whether or not to design in a significant amount of maintainability. What are the factors needed to be considered? You might want to stop the presentation for a moment and think of these considerations, but I'll show you a listing on the following slide. And here's the solution to exercise 1M, stating the factors that need to be considered related to maintainability. I'll let you review these at your own pace. Maintenance and maintainability continued. So we need to be careful when designing, for example, electric drills, the ease at which they can be maintained and serviced. This might be of importance to the average DIY enthusiast, maybe considering the ease at which the parts can be obtained and can be assembled or disassembled. The service life of the product, life of the component parts also needs to be established so that we can make informed decisions about the need for maintenance. So when designing for ease of maintenance, we need to consider the extra costs that are involved using more sophisticated manufacturing processes and component parts, and balance this against the customer satisfaction of the finished product or system. Requirement 5 in our list is the target product cost. Here's design and manufacture cost. A realistic product cost needs to be established early on in the design process by negotiation with various stakeholders. It's sometimes found that the estimates for products or systems are often set lower than reality dictates in order to try and gain a competitive advantage. However, we need to be careful in accepting or stating unrealistic estimates because this approach can potentially put the business into debt. And design engineers need to be aware of how to accurately estimate costs and financially evaluate the viability of new ventures, new products, new systems, etc. Exercise 1C here. Question posed is how could a realistic product target production cost be achieved? Perhaps you might want to take a moment here to stop the presentation and think about the various approaches that could be adopted to try and estimate a realistic product target production cost. I will show some suggestions on the following slide. Exercise 1C. The suggestion here is by assessing costs of existing or similar products currently on the market, that the overall budget will cover various unanticipated expenses. Unexpected or unrecognised costs can be fatal to the product and even a company's long-term prosperity. Here's operation and service costs. So not only design and manufacture costs have to be considered, but in service costs should be carefully estimated to ensure that once the system or product is installed, it's commissioned and is operating, such issues as servicing, maintenance and repair have been assessed financially. An acceptable operating cost could significantly reduce expected profits and ultimately cause a service to be curtailed or indeed a company to collapse. Requirement 6 in our list is transportation. For example, consider the consequences of designing and assembling a very large 100-ton transformer in Glasgow, Scotland, and transporting it to a power station in Penzance, England, a distance of approximately 470 miles. The cost and practicalities of transporting such a structure would make the task prohibitively expensive, if not near impossible to achieve. Exercise 1T here. Under what considerations does a product become costly to transport? Some hints here. Consider a very large product, a very heavy product, or a very dangerous product. For a moment you may want to think about the considerations involved with such products. Some suggestions are stated on the following slide. Exercise 1T. Here are some suggestions. I'll let you review them at your own pace here. Item 7 in our listing is manufacturing quantity. Due consideration needs to be given at the design stage as to the ease of manufacture of products and their associated parts. The cost implications of over-engineering must be remembered when designing, particularly with respect to detailed design, For example, don't over-specify surface finish requirements, surface treatments, etc. Component parts should be designed with a focus on saving costs, and all non-functional features and any excessive trimming from the part should be omitted, again in an attempt to save manufacturing costs. Here is exercise 1N. What do the following manufacturing terms mean? The term jobbing relates to one-off production, for example, shipbuilding, tunnelling, building bridges, water treatment plants, etc. They tend to be seen as one-off items. Batch production, this relates to such products as aircraft, electric motors, petrochemical valve manufacture, etc. Here we might have batches from say 10 to 50, maybe to 200 to 500, depending on the particular product. And mass flow production, this is associated with products such as car assembly lines, ball bearing manufacture, production of bolts, washers, nuts, fizzy drinks, etc. Manufacturing quantity continued. We also need to determine whether our items are being bolt in, sometimes referred to as bolt out, assembled using standard parts, manufactured in-house, manufactured by others, or manufactured on site. This will again depend on the philosophy adopted by the customer, the manufacturer, and the resources available. For example, workshop facilities, tooling, workforce capabilities, etc. Design requirement 8, aesthetics. This is a consideration once all the primary requirements regarding function, safety, use and economy have been fulfilled. As regards aesthetics, the aim of the designers is to create products that appeal to the customers. Thus, industrial design can be considered to lie between engineering and art. So, for aesthetics, consideration needs to be given to the shape or the form, the use of colour and the surface texture. And sometimes the aesthetic design of the engineering product or system may be actually outside of the remit of the engineering designer, and specific expertise may be enlisted to help in this regard. Aesthetics continued. The specialists, such as graphic artists, would be seconded to the design team to assist with product aesthetics, packaging, labelling and graphics, and for designing for a particular market. Requirement 9 in our table was legal implications. Legal implications relate to including various legislation, UK, European, international, and of course legislation must be considered at the early stages of the design process, and the engineering designer should have an understanding of the law regarding patent and copyright protection. Legal implications continued. I'll let you review this slide at your own pace. Here's exercise 1L from my notes related to description of contracting law. Requirement 10, health and safety. Adherence to various regulations and standards has to be undertaken. Here's design requirement 11 related to quality and reliability. I'll let you review this slide at your own pace. Quality and reliability continued. Requirement 12 in service life. Requirement 13 relates to competition. In other words, understanding who your direct competitors are and what patents or products are on the market already, and in particular how any proposed outline specification for a new product indicates any significant difference to any similar products on the market at this time, and if so, it's very important to understand the reason for such differences between the proposal and what's existing on the market. Does the proposal offer a competitive advantage, or are there valid reasons why these new proposed differences have not already been included within the products existing on the market? We don't want to reinvent the wheel or overcomplicate the product for no significant gain. But in some products, the old adage of keep it simple, stupid can sometimes be the best approach when modifying a design. Requirement 14 is packing. The packing cost, of course, will add both product cost and product volume, but obviously packing is useful because it protects the product against environmental effects or off transportation. ingress of water, corrosion, shock loading, accidental damage. Requirement 15 is manufacturing facility. Is the current manufacturing facility a constraint to the design? For example, limiting the manufacturing processes that can be undertaken. Do we manufacture components in-house or employ a bolt-out policy for standard items? Certainly applicable to bolts, nuts, washers, springs, hinges, specialist items. Sometimes subcontracting for specialist sub-assemblies may be beneficial. For example, door locking mechanisms might be undertaken by specialist manufacturers. Requirement 16 is size. Consider any size restrictions on the product. Ensure that the product will fit in allocated spaces, or be careful that they actually fit, but then do not allow space for maintenance, servicing or repair. Sometimes that can happen with car design. They can be assembled in the factory, but when the car mechanics have to work on them, sometimes it's very difficult to access certain parts of the engine, or maybe the whole engine has to be removed just to replace a water pump, for example. Does the product size and shape cause handling or storage problems? Requirement 17 is weight. What is deemed the desirable weight for a component? In some industries, weight can be directly related to costs, such as in the aerospace industry. And as with the size consideration, weight can cause handling problems on the shop floor, during manufacture and assembly, or in transit, during installation, or when in use with the customer. Sometimes using a modular construction to reduce size and weight problems during various project stages is also considered. Even lifting points may sometimes need to be designed into the product. Requirement 18 is materials. Sometimes the customer states the materials, but if they're not stated by the customer, then the design team are responsible for deciding on preferable materials. Sometimes special or exotic materials might be required. These can sometimes specifically be specified by the customer. For example, very large companies in the aerospace sector will often specify particular materials to use. Obviously, we avoid toxic materials these days. Lead-based paint, for example, should not be specified. Requirement 19 is the product lifespan. Is the product expected to last 1 year, 3 years, or 30 years? Because that makes a significant difference to many aspects of the design. So requirement 20 relates to standards and specifications. As mentioned previously, there are many standards that a product or system has to comply with, such as British standards, European standards, international standards. Sometimes a cross-correlation of these different standards needs to be undertaken prior to commencement of the design process, as it can be difficult, costly, time-consuming, and indeed inefficient to attempt to retrospectively match final designs against various standards. Requirement 21 is the actual customer. Customer contact and input is essential to the success of the product, although much contact will be online these days using various IT platforms. Sometimes face-to-face discussion, allowing for question and answer, can be very useful. Also, examination of competitor trends and specifications can also provide useful inputs to the development of the product design specification. Here's requirement 22 relating to shelf life or storage of our product. The shelf life consideration can sometimes be overlooked within the product design specification. Shelf life must be specified at the outset to combat decay that might occur to the product whilst in storage. For example, seized bearings might occur, corroded gearboxes and screw threads, perished rubber seals. Electrical circuits may suffer from moisture ingress or contamination, etc. So we need to clearly stipulate shelf life within the specification. Requirement 23 is processes. I'll let you review this section at your own pace. Section 23, processes continued, and I'll let you review this slide at your own pace. Is requirement 24, timescales. Timescales may relate to the overall project timescale or to phases of the project. For example, the conceptual design phase, detailed design phase, production, assembly, test, etc. Long lead time items should also be carefully assessed. This may relate to, for example, complex forge parts or specific electronic equipment that, due to their complexity, that may not be available until the production or manufacturing processes are underway. So we need to account within the timescales for the delay in these long lead items being delivered. For example, an aircraft undercarriage is usually produced by forgings, but these have a very long lead time, so maybe the first 6 aircraft off the production line may require to have machined undercarriages to help account for the long lead times of the forgings. But that might require some different design considerations and different analyses, etc. All this needs to be accounted for within the project timescale. So essentially we're trying to ensure that the product is effectively and efficiently designed, because lack of adequate design time, certainly in the initial stages of the project, has the potential to lead to significant cost overrun in both time and money. Requirement 25 is testing. Most products require some form of testing after manufacture. This can take place either in the factory or on site or at both locations. I'll let you review this slide at your own pace. Testing requirement continued here. Read this at your own pace again. Requirement 26 is company constraints. Read this at your own pace. Item 27 is market constraints. Requirement 28 relates to patents, literature and product data. Requirement 29, political and social implications. Requirement 30 is installation. Installation must be considered within all specifications. You read this at your own pace. Requirement 31 is documentation. Documentation continued. Requirement 32, disposal. Very important these days. Let you read this at your own pace. Requirement 33, public acceptance. Public acceptance continued. Public acceptance. Final slide shown here. Requirement 34, training. Will training be required, such as training associated with manufacture and assembly methods? Maybe there are new special procedures, techniques required in the production of the product or system. Will there be training needs during the installation phase, whilst commissioning and setting up the new product or system in the workplace? Is training required for the usage and operation of the product or system, for maintenance, repair and servicing, or ultimately with decommissioning, recycling, disposal, etc.? Will ongoing or updating training be required during the product's lifespan? Again, all these training needs should be fully considered and outlined within the product design specification. Requirement 35 is ethical design. 36 here is ethics. This often relates to codes of practice for engineers. In the UK might be produced by the Engineering Council. Requirement 37, use of prototyping. Prototyping continued. This slide states some of the benefits of prototyping. Here's a prototyping slide. Final prototyping slide. Requirement 38 relates to quality control, quality of the product. 38, quality control. Review this at your own pace. Some of the standards mentioned here may be superseded now, but I'm sure if you research these specifications, you'll find the new and relevant standards. Again, some of these standards may be superseded, but there will be replacement standards that you can find from your own research. Requirement 39 is actually quality assurance. I've termed that here the quality of the process involved. Quality assurance continued here. Quality assurance continued. Quality assurance. Here's some of the criteria. And hopefully the aim is for a right first time product. Quality assurance continued here. This slide relates to the importance of the engineer keeping adequate records throughout the design process. Just some suggestions shown here on this slide. Quality assurance continued. This slide relates to the deliverables that students have to produce when undertaking college project work. Quality assurance, continuation. Some quality assurance references here. Again, there may be more up-to-date standards to research. And purely for background information, and to conclude this presentation, here's a flowchart of the overall design process the students have to undertake, outlining the various stages from the initial needs assessment right the way through to the final presentation to a technical audience. And within this process, both an initial outline project proposal and a project design specification were undertaken by the students, and once developed, the PDS formed the basis of all the various activities, from generating design concepts through to selection of concepts and production of the final technical report. Hopefully you can see the relevance and the importance of the PDS to the entire design process. And during this process, our students had to undertake various design reviews. There are 3 design reviews scheduled throughout the 30 weeks. Initially, the preliminary design review, which encompassed the development of the product design specification. An intermediate design review, this was usually around the conceptual design stage as we enter into a detailed design stage. And again, the PDS was a very relevant document to refer to within this stage of the process. And we had a final design review very near the end of the project process, once the technical report and the presentation to an intended audience was undertaken. And during this review, the PDS formed an important underpinning aspect of this review, ensuring that all design criteria had been achieved, and if not, clearly justifying why not. Here's an enlarged view of the various design reviews. The questions stated on the slide here are purely for the students' reference to help them try and generate the agenda for the design review which they had to attend. Here's the intermediate design review. Again, some considerations for the students to help generate their agenda. And of course the final design review. Again, just a few hints for the students to consider when developing the content of the final review. So here's the bibliography used to help underpin this presentation and the contents therein. Very good reference sources. I look forward to seeing you in the next presentation, where we use the knowledge and the structures as outlined in this presentation to try and show you how to develop and structure a product design specification. As always, thank you for viewing.